Go.
Hello, good morning, everybody. My name is Niccolo Giannelli, and I work for Stratasys, following the aerospace industry in the whole European region. The objective for today is to talk you about Stratasys solution for the aerospace industry, and specifically the benefits that Stratasys is bringing to the MRO side of this industry. In these days, when we see that the aviation, and especially the civil aviation, is facing new challenges, and so we are offering solution to win and to successfully face these challenges. Just a couple of words on Stratasys for those of you who don't know this company. It's one of the first companies to enter the world of additive manufacturing, and it is now nowadays 30 years, more than 30 years actually, that Stratasys is on the additive manufacturing market. During this time, you see, we reached big numbers. So we have more than 18,000 customers, and we have more than 140,000 machine installed. So besides these big numbers, so our heavy presence in the market, I'd like to point out the number of patents. So this is extremely significant, pending or already registered. This is extremely significant and giving an idea of how much we focus on innovation and on continuous improvement. As I said, we have more than 1,000 patents and a few technologies, but today I will focus mostly on the FDM technology. So it's a filament-based technology working with thermoplastics. This is the technology on which I will focus today because this is especially suited for aerospace. Indeed, since it uses the real thermoplastic, the performance of the material will allow the technology not only to produce concept models or prototypes, but also to go in a more interesting field of application, especially for MRO, like manufacturing tooling, jigs and fixtures, and end-use parts, in this particular case as repairs. So let's start deep diving immediately without any other introduction in the aerospace manufacturing with FDM and with the Stratasys solution. Just one slide on the system to have an idea of what we are talking about. These are the Fortus class machines from Stratasys, and these are the machines that are suggested for aerospace. Because they have a solid structure, they have steel structure, a great thermal management system, so a thermal distribution inside the build chamber, which is controlled and certified. And so all these characteristics of the system make them capable of processing in a correct way all the material, and especially the high performance material that are required by aerospace. You also have an idea of the size of the build plate, or let's say the build envelope of this system. So from 400 millimeter to the very big one of 900 millimeter. When we talk about aerospace, when we talk about application, we cannot skip talking about materials. So aerospace is naturally an industry where we position ourselves in the high performance segment of the material. And so you see that Stratasys is present in this specific segment of the material offering with four principal material, but it's not only that one. So we offer also standard plastic and engineering plastic. So the choice will be up to the user, depending on the application. So if it's a standard prototyping, you will use standard plastics. If you're using a high performance composite layup tool or parts that are flying, you will use a high performance material. So let's see which are the options in this particular part of the pyramid. We start with the ultim 9085. So this is the aerospace certified material, the material that most of our customers are using when talking about flying parts. Why? Because this has been tested and certified versus the flame, smoke, and toxicity requirements of the regulatory bodies. In addition to that, so it's capable of meeting the requirements from a flame, smoke, and toxicity standpoint. It brings together high strength to weight ratio, so it's a really stiff and tough material. It has a high heat deflection temperature, so it can go up to 153 degrees during its usage, and it is fully traceable. So this is very important when talking about certified parts. You can trace the material back to the producer through all the steps that it took to come into your hands and into the final parts. So the top user application you see are aerospace interiors and production parts. Another material from the ultim family, a different blend, is the ultim 1010. So this particular material has higher thermal and mechanical properties than the ultim 9085. And these properties makes it the material that is used for the application that you see in the picture here in the top right. We are talking about composite layup tooling. So this material is not only resistant, is not only highly performing from a thermal point of view, it can bring all together and satisfy the requirement from an autoclave cure cycle in aerospace, and we will see some example. Now we shift from the ultim family to the polyamide family. We recently introduced a really strong material, so it's nylon 12 loaded with chopped carbon fiber. So we are talking about composite loaded material, even if with chopped fiber. This is the stiffest material that we have, and has the highest also stiffness to weight ratio. So these characteristics make this material particularly usable for the application that you see in the pictures here on the right. So on the top, sorry, you see the drill guides for drilling operation in MRO, or also in assembly in the final assembly lines of the aerospace products. And on the lowest picture, you see a pattern for the sheet metal forming. We will see also some example from any of the application that I'm showing now in this brief summary on the materials. Last material that I like to express, to talk about expressively today is the Antero 800NA. So this is a PEC-based material. So Stratasys recently entered into this polyether ketone-ketone family. And this is the material that brings together, again, with high chemical, high mechanical and thermal performance, it brings the highest chemical resistance between our material. So until a few months ago, we were able to face the quite aggressive material, but after the introduction of Antero 800NA, we are able to face also the strongest material from the chemical aggressiveness point of view. In this case, I'm talking, for example, about Skydrol and these kind of hydraulic fluids. So this material is the material that should be used when we are talking about ducting for these kind of components, for housings also, like reservoirs or tanks, and moreover for electrical conductors. So you see in this picture the 10, the natural color version, but we have an additional version which is black, and it is with carbon nanotubes with specific electrostatic dissipative properties. So it's an ESD material that can be used for electrical applications. So we have seen briefly the systems. We have seen the materials that are mostly suitable for the aerospace MRO application. Let's deep dive now into the application, and let's see what you can really do and why Stratasys is the best choice for this kind of application. On the left picture, we see the, let's say, well-known application of the additive, so I won't go too much in detail. It's rapid prototyping, so designing, functional tests, and surrogate parts. Let's move on the other part of the slide, which is the most important in my opinion. So on the second and third picture, we see rapid tooling. One example from Spain for the NH90 helicopter assembly line, It's an assembly tool, the second picture. So you will see in the next slide how this is a big tool printed in one piece with included features to drill and to position our components, really easy to handle by our operator. And so it's bringing together all the advantages of additive manufacturing. The third picture is a composite layup tool. So now we are talking about ultim 1010, and we are talking about tools, rapid tooling to produce our composite parts. So we see how we are able now to produce composite tool in a faster and cheaper and a better way than before with additive manufacturing. The fourth and the fifth picture show end-use parts. So I will not talk too much now about this. We will see them later, but consider in MRO operations also that you can not only produce your tool with additive manufacturing, but you can produce your end-use parts. So spare parts replacement and parts to be installed into the aircraft. So let's have a look at some examples. As I said before, assembly tool, drill guides, jigs, and fixtures are one of the big family of the application for aerospace MRO. So you see in the top picture an operator using a drilling guide manufactured with our polycarbonate material. Depending on the loads, on the vibrational loads during the drilling operation, you would choose a more stiff material. So if the loads are high, if the frequency is high, you may choose nylon 12 CF. In this case, it was not required, so they used polycarbonate. In the lower picture, you see how ultim 9085, another material, was used for assembly tooling. And you see also how it is combined with the traditional technology. For example, on the left picture, the complicated, small, and otherwise expensive and complicated to make parts are made with additive manufacturing, simplifying it, making it faster and cheaper. The traditional shape, so the extruded aluminum part, is made with traditional technology. They are combined together, you maximize and optimize the advantages. So the example that I've said before is particularly significant. It's from ULA, so United Launch Alliance, and was used during the assembly of this rocket that you see in the picture. The very important data here, you see in the center of the slide in the table, is the lead time reduction. So before, ULA was forced to produce the parts in-house or to ask for the help of an outside, of a third-party supplier, and it was taking up to 4 months. With additive manufacturing from Stratasys, so it's taking only 10 days. Why I say from Stratasys? Because only this kind of machine are so reliable, so consistent that you can be sure that your part will be printed in the form that you have in your design. So you don't need to try maybe 2 or 3 times to have the end-use parts that is responding to the request. No, with this machine, you directly print the part and you are sure about the results that you will get. Another very important application for MRO is sheet metal forming. So many times we have the old school aircraft made in aluminum or with a huge use of metal components. You may need to repair some of them. And this is the particular case of the top picture that you see here in this slide. This is a repair for a frame of the fuselage of an Harrier jet. And it was done with polycarbonate. So thanks to the high compressive strength of our material, you can produce these patterns for rubber pad forming or either hydroforming at high pressure. Then you can use this pattern to produce the shape of your metal parts. So not only frames that you see in the top picture, but also panels that you see in the lowest couple of pictures. Also here, the advantage is extremely big, the advantage that you introduce with the additive manufacturing. So you have more than 50% advantage, so reduction in terms of economics. So you save 50% of the cost that you were spending before, and you get the tool in few hours again instead of days or weeks. And we all know that when we are talking about repair, this is extremely important to be able to repair our part and send back the aircraft to the air again as soon as possible. Another example for the foaming tool in MRO operation, you see a couple of tools in the top picture done with nylon 12 CF. So you can recall the thing that I said a few minutes ago. Depending on the requirements of your manufacturing procedure, in this specific case, the pressure of the rubber part or of the hydrofoaming machine, you can choose the material that best suits for your requirements. In the lowest picture, we see the example from BAE Systems. So it's again a Harrier jet fighter, and they have done the pattern reducing the cost from $3,500 of the traditional tool to only $133 with the Stratasys Additive Manufacturing tool. And also the lead time was reduced from 21 days to less than 20 hours. So you see here, we are talking about even more than the 50% of the previous slide. We are talking about a cost saving of 96% and a time saving of 95%. And this is very important in MRO, because we need to finish as soon as possible our operation to have the aircraft fly again soon. Next application, and this is the one of the most advantageous also in tooling, is the composite layup tool. So we see the two pictures of an ultim 1010 composite layup tool that is capable, as we can read in the text, of reaching 180 degrees of temperature together with 7 bars pressure. So this is the cure cycle parameters for most, or the majority of the composite carbon fiber components that are used in aerospace, and that makes Ultim 1010 and our very precise and very repeatable systems suitable for the production of a composite layup tool. So here is another example why Stratasys systems are the most, or the best one to do this kind of components. When we are talking about a composite layup tool, we all know that the tolerances are quite tight, and so we need to have a stable and a solid, robust machine that is able to meet these tolerances. This is once again possible only thanks to the thermal management inside the build chamber that Stratasys has been able to develop and perfection during the 30 years of experience. So Stratasys is today able to give to its user a machine that is capable of delivering the results as they are needed. And this is not possible with other kind of machines. One example from one of our customers, it's Dassault in their Falcon Jet program. You see on the left top picture, the tool, the composite layup tool that was used before and has been used to evaluate our technology. So this tool was done taking around 16 weeks of time before and costing around $25,000. The tool that you see below the traditional one has been realized with Ultim 9085. You also see the internal structure that makes easier the transmission of heat inside the autoclave, and so it makes even quicker to reach the exercise temperature of the mold. And this is very important to have this kind of structure internal to the mold. Also, it makes the tool lighter, and so our operator will be able to move the tool with the hands instead of using the forklift, for example. And you see also the forklift preparation in the upper picture. You see these two locations for the forklift. The tool below, done with the Stratasys machine, was realized in only 1 to 3 weeks, and in only spending only $5,600. So we see a huge reduction both in time and in cost of the tool. On the right, we see another positive aspect of our machine. So we have seen at the beginning the two systems, so the Stratasys Fortus 450 and the Stratasys F900. Changing material inside this system is extremely easy. It only takes a matter of minutes to half an hour to complete the whole operation of changing the material. With the other material, you can produce all the tool in the family of the tools needed to produce the composite. I'm specifically thinking to the device that holds the mold during the layup deposition, or the guide that you use when you need to trim the plies of the composite material. All these tools, you see, are bringing additional advantages. So creating all the environment and all the tools that you use during the production could cost $30,000, while doing all these tools and improving also all these tools with additive manufacturing will cost you only around, let's say, between $4,000 and $5,000. We see a huge decrease of cost and time also in this case. Here is another example, still MRO. So there was a damaged antenna cover to be replaced in the nose of this helicopter. And you see that the mold was done on the top right picture. You see that the mold was done using ultim 1010, using a Stratasys machine. As I said, and from the example in the previous slide, not only the mold is realized with our technology, but also the tooling required to do all the steps of these production process. So in the lowest right picture, you see, for example, the component that was printed to trim and to drill the composite part afterwards, after the cure cycle in the autoclave. Another application that we have developed quite recently, actually, it's one of the last to have been developed, and has been widely used in the engine MRO, is the masking for high temp spray, or also for painting. So we see in the picture some aerospace components, some engine components that during the MRO phase sometimes need to receive some kind of coating or some kind of painting. We all know that the procedures are very detailed, and the coating doesn't always have to be applied to the entire surface of our component. So you need a mask to cover the parts that don't need to be coated. You see in the low left picture how this was done before. So it was manual taping. It was requiring a lot of manual work, and it was also less predictable and less precise. Doing this tool, printing this tool with additive manufacturing, determines a huge cost saving in terms of thousands of euros for every single engine maintenance operation. And is also capable of avoiding any error that can occur during a hand operation. We all know that a hand operation, a long hand operation, can bring always error with itself. One note from my side is that these spray masks are usually used at a very high temp, so they require high-performing material. So this is another reason why you need to use a Stratasys machine for this application, because you need a component that can reach up to 200 degrees with dimensional stability, which is not achieved by other kind of machines or other kind of materials. You will use ultim 1010 in this case, and you can easily complete this MRO operation. Another problem that we can think about during our maintenance, repair, and overhaul operation is that we may damage our structure during the operation. And this is the specific case that you see for this titanium pintle fitting. You see on the right that this area is often hit by the operator during the MRO operation. So this is Gartner Aerospace, and they have been able to avoid this €1,000 and a couple of hours rework time when they make this error by printing a cover that they have designed with the exact shape that they need during the operation. So nowadays they put the cover, they do all the operation, they take away the cover afterwards, and they see that there is luckily no damage, and there is no associated cost and time of repair after the damaging. Another few example, we see GKN Aerospace on the left, they use our machines to produce tooling that have not only an economical advantage and a time advantage by using Stratasys Additive Manufacturing, but they would also not be possible to produce with standard technology due to the particular shape or extremely complicated shape that they have. On the right, we see another example from BAE Systems. We see a very big tool in this case, and this is a protective cover for the floor of a Typhoon fighter jet. Also, in this case, we are talking about military application. This is a cover that they use during the operation. One piece, one protection step, and then they can do all the MRO operation without damaging, in any case, the floor. This example is one that I brought to particularly highlight how additive technology can be an advantage when you use it from the very beginning step of production. So in this case, it's Boom Aerospace. It's a new company. They are trying, for those of you who don't know them, they are trying to step again into the supersonic flight for the civil aviation. So their project is completely new. It's blank sheet, and they are thinking additive already from the beginning. So this particular component that you see for the exhaust from the engine has been designed to be manufactured specifically with our FDM machine. And you see in the table here in the slide how this leads to even higher cost and time savings. So we're talking about 98% in cost and 95% in time. So thinking additive really maximize the advantages of additive that we can have. Also in this case, of course, it's an exhaust. It's in the exhaust line of the gases, so you need to have a material which is capable of withstanding high temperatures, and which in this case you see it's an ultim 1010 component. So once again, we are talking about a material capable of withstanding 210 degrees. Another aspect that I wouldn't underevaluate is again additional to the cost and time reduction, is the part count reduction. So thanks to the capabilities of additive manufacturing machines, you can join together components that before you couldn't manufacture altogether. And this is particularly evident in this case. So we see the part count in the lowest picture, traditionally manufactured tool, was around 140 components. And now with 3D printed parts, we are talking only about 16 components. So a huge reduction, and also a huge reduction in all the operation that you would otherwise need to assemble all together. And remember that during assembly operation, you can always make errors. And this is not counted into this cost and time saving. Last chapter of the presentation today is the usage of Stratasys FDM as the only qualified technology for aircraft components and in MRO operation, specifically for repairs. Stratasys has been able to qualify the technology thanks to the improvement that it brought to its own system. So we see in the chart here how we were able from the beginning status of the technology to come to the current status of the technology, increasing the nominal value, so the strength that we can reach with our material, but also decreasing the viability of the results. And so we made our technology the only one as consistent, as repeatable as required by the Federal Aviation or by the European Aviation Safety Agency to produce parts for the aircraft component, to fly on aircraft. So repeatable, precise, really highly performing technology is the only one that can be used in a qualified way to produce interior components. I won't go too much in detail. I will just mention the qualification program is the NCAMP. So we have been following a composite material program qualification process, and all the data are publicly viewable. You can view them on the NIA website. So it's all published, it's all public. We have qualified our technology. We go directly to the application. So we see some example from one of our most famous customers. This is Airbus. And you see a lot of components with very different shape and very different location inside the aircraft that have been manufactured with our technology. So this makes the fact that you can get these components spending less money, but more important, in less time, you can produce them in less time. This makes the FDM technology an extremely suitable technology for MRO operation. So once again, if we think that we have to substitute this panel cover because it has been damaged by a luggage of a customer, I don't know what can happen, but maybe we need to replace this cover immediately. Then we can print this part in 10 hours and we can have the part mounted the next day, instead of ordering the parts to the vendor, to the OEM, waiting 3 weeks, spending a lot of money, and slowing down all the steps of MRO. We see some examples here from China Eastern. They have done a lot of components actually on several programs. So we see the Airbus A330, the A320, the Boeing 737. They have a huge fleet and different kind of aircraft. They can use the same machine to produce the component for any kind of aircraft, because they are not limited to a single program with this machine. We see that, for example, for the newspaper holder and for the iPad support for the pilot, they save 90 to 96% of the time. So 3 days, starting from 85 or 35 days, and they save between 50 and 75% of cost. So not only the time, but also the purchase cost is highly reduced from the starting point. Yeah, that was all from my side. So we have seen quite a lot of application that you can remember with the same machine and with a quite consistent approach.
Yeah, so thank you, Nicolo. Thank you for your wonderful presentation. It was very clear and very interesting. And we can start our brief Q&A session, because we have some questions from the audience. Okay. So first question, do you think that it will be the current suppliers for jigs, fixtures and tooling that will upgrade and include these technologies on their portfolio, or it will be mainly through new players?
I think, and actually it's based on my experience on the field, that both the roads will be taken. So I see the vendors, so the OEM having in-house machines to supply and maybe to cover some over demand for some kind of parts. So maybe they have their production line set up for a certain amount of components for one kind of components. Maybe some additional order come and they would not be able to satisfy this request. So they use additive manufacturing to satisfy the requests. But on the other side, I also see the customers, and especially those that have DOA, so design organization approval from the authorities, internalizing the technology, developing their own design and producing their own parts. Because don't forget that you can also customize your parts and your design if you have a DOA. And then, of course, a POA to produce parts to meet in a better way the requirements from your usage. So I see both the things, and this is actually good for us because we will have as user both the Airbus and Boeing, or the airlines or the airline suppliers.
Yes, of course, diversity is always welcome, right? And question number 2. Taking into account the rate of development of these technologies, when do you think they will become mainstream for these applications?
That's a very good question. I hope as soon as possible. I mean, we know all that we are facing a very hard period in this year, especially for civil aviation. If we can find one positive side, is that when you are facing a hard period, you need to find a new solution. So between all the bad news, I think this will be a push for all the companies to find new solution, and additive manufacturing is actually one of the best solutions available today to overcome these these challenges of today. For example, I think about the closure of the borders. If you can have your small production machine in different locations, you don't need to ship components between one and the other country. If I think to the challenges also, for example, of the intellectual properties, you don't need to send away your design. You can produce in-house, so you don't need to send your design and your intellectual property to a third party. And also, for example, now we see a reduction in the volume of passengers, of flights, and of course this will mean also a temporary, at least, reduction in the amount of components and of repair parts that will be required. So instead of resizing your production line, you can use as a bridge the additive manufacturing during this hard period. So I see a lot of challenges in aerospace, but I think that these challenges will bring the moment of additive manufacturing as a mainstream technology closer. So I think this will happen soon, thanks to, unfortunately, this bad period.
Mm-hmm. So within a short term, you mean a year, 2 years?
I mean, in the new program, yes, I think and I know that already the companies are considering these technologies. So if we consider from the moment you start the program to the moment you deploy, it's between 1 and 5 years. I think that additive will be heavily used for aircraft industry.
Okay, thanks for your insight on this question. So we have questions coming, more questions coming. So I'll jump to question number 3. There are some concerns about the environmental impact of 3D printed products. What's your opinion on that?
I am also concerned, and I'm happy to work at Stratasys from this point of view. Because this is a filament-based technology, as I said at the beginning. So this naturally brings to reduce the waste of material. So the material that you use and you produce, of course, is only the one you require to produce your parts. Remember that more material means more cost. So none of our customer is wasting material if it's not required. Additionally, since this is a filament, we don't have grains of powder going away or to be filtered by air filters. So we also eliminate this step in the production. Additionally, we are not talking about end-use parts now, because for these parts we will always use materials with high performance, but for the low-end materials, the bio originated material are increasing. So for example, we think about PLA, it's a heavily used material also from our printers. This is completely biomaterial, so it's biodegradable, and it doesn't have an impact on the environment. So as I said, I'm happy to work at Stratasys because both the waste and the nature of the material makes us one of the most environmentally friendly vendor of additive manufacturing machines.
Okay, well, I'm saying that we should have invited you to yesterday's conference, because we addressed this issue of sustainability, and of course it's the main topic. And very relevant. It's a very relevant question. And now I will jump to the 4th question. So do you know how have Portugal embraced these technologies up to now? Do we have the right mindset?
Actually, yes. So I would say that Portugal is perfectly aligned with all the other European countries. Especially, now we shift a little bit from aerospace. So we know that Portugal is one of the biggest countries for injection molding. And from this point of view, you have started already a few years ago thinking about additive manufacturing. So it has started to enter in the people mindset already a few years ago. And so this makes Portugal perfectly aligned with other countries, if not even better than other countries. From the aerospace point of view, you have a couple of very important industries there. I wouldn't say any name, but I have been in contact with them. And also from aerospace point of view, I think the mindset is good. and the country is ready to be part of this revolution, and we will see the results very soon, I believe.
Okay, great. And I have another question yet. So, and we have time, as we can see. So, I will take the opportunity to let you know the fifth question. Many of your examples are for MRO organizations. These solutions can be applied for POA organization for jigs. How the tools behave in terms of fatigue after a large number of cycles. So two questions in one.
Yeah, it's a very interesting. I'm happy because we go a little bit technical. As I have an engineering background, I'm always happy to speak about these technical topics. From the point of view of fatigue, I have to say that talking about thermoplastics, there haven't been the same testing campaign as for the metal that we are used to. Also, this technology has been used for this kind of application in the last, I would say, 5 to 8 years. So we don't have all the literature of data available to determine the fatigue data. Besides that, depending on the application, we have different performances. So I have, and also it depends on the requirement from the single application. So particularly if I think about the foaming tool, for example, if we are using a higher pressure, we will decrease the life of the tool. Let's say that we have example and bibliography on our website, and we can and the audience can always access these data, can always ask me directly, but depending on the geometry, depending on the requirements, we have a different behavior of our material and of our components. We can range from 10 cycles for example, a very demanding injection molding tool, so high pressure, very abrasive material. But when we go to aerospace, we are more in the hundreds number of cycles, either for the composite layup tool, either for the, and also for the foaming tool. For the drill guides, we are also located in this amount of operation. And if we think about aerospace, this is perfectly aligned with the amount of components that we have to produce, the amount of cycles that we have to face during our maintenance and repair and overhaul operations.
Okay. Okay, great. Thank you, Nicolo, for this insight. So we have run out of questions. So I don't know if you want to finish with a final word or reinforcing some keywords of your presentation, so we can say goodbye and pass on to the next session, since we have time, which is an unusual thing. But I believe that the digital, making this digitally always provides a more secure timing, you know, because people don't
yeah
they just talk, they say what they have to say, and everything is much more clear without any unpredictable things happening. So Nicolo, do you have any final words?
Yes, it's a good and bad side of the digital event. I mean, you don't have the interaction between people, which is always a pleasure, but on the other side, you don't get interrupted and you're quicker. No, for sure. One thing is to thank the audience for participating and for the very good question, actually. I was happy to answer to these questions. I just want to underline once again that additive manufacturing is a new technology and is enabling to face the challenges that the world is presenting us, the challenges that we have seen and the challenges that will come. So it's important to get into this world as soon as possible, because by being there, you develop your know-how. And by having this know-how, you will be even more efficient in facing the problems of the future. So as soon as you get schooled, the better you will be able to take profit from this kind of technologies.
Yeah. Okay. Nicolo, once again, thank you very much for joining us and for your wonderful and very clear presentation. And we will see you next time, perhaps in the next edition of the AED Days, since you are a repeated. You were with us physically last year.
It's a pleasure.
Yeah, so let's hope we can manage to be present next year physically in the AED Days 2021. Thank you very much, Nicole. Thank you.
Thank you, and have a nice day.
Thank you. So without